Hello, and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and if you listen to part one of this two-part episode, you will know that my guest today is a Schmidt Science Fellow at Stanford. She's done some fabulous work on distributed and localized model predictive control, which we covered in the previous episode, but for the next hour or so, we'll be focusing on a very different strand of her research interests. She has done a bunch of super interesting work at the intersection of AI and control. When I first saw her speak about this at a conference last year, it honestly blew my mind. Her work is so cool, her papers are so well written and very accessible to people from a control background. She is amazing. So, buckle up and get ready to learn all about AI architectures, using tools from control to analyse and design AI systems, controllability of large language models, integrating LLMs with traditional controllers, using AI systems for robotic control, and much more with my guest for this episode, Dr. Carmen Amo Alonso.
My name is Carmen Amo Alonso. I'm currently a Schmidt Science Fellowship doing my postdoc at Stanford, and I'll be an incoming assistant professor at UC Berkeley in 2027. I work in the intersection of control theory and AI.
So, since your PhD, you've kind of moved areas and written a bunch of really interesting papers at the intersection of control and AI. I guess my first question is, how did you end up doing research in this area, and why is it something that interests you?
Yeah, so it was a bit random, honestly. I was really interested in language, like human language, ever since I was a kid. My dad was a linguist, and so I don't know, I just had this curiosity. And my advisor, John Doyle, really is really all over the place with his applications, like all the way from neuroscience to biology, physics, everything, right? But he never talked about language. So for years, I kept saying, John, what about language? Like, can we do something in language? Can we? And he would ignore me initially, and then finally, and I kept finding stuff and sending it to him, and like he would completely ghost me. And then eventually I found something it's called The Architecture of Language by Jack and Duff, and even the title really resembles like the way John thinks about things and the keywords he uses. So I sent him this video and he really liked it. And then that sort of started us in this conversation about human language and how that can be modeled as a control problem and so on. And it was right at the time when ChatGPT became a thing. I think it was 2021 or 2022, when, yeah, all these chatbots were just like blooming. And so I thought, well, what if I study human language in this context? It seems like a really hard problem, like a really pressing problem for society, right? Like we're going to have these chatbots everywhere, and these things should be made controllable, and we should be able to control their output instead of having them be black boxes. Also, they're very large scale systems, which is sort of where my expertise lies on for control. So then it just felt pretty natural to work on LLMs, and then that led to all sorts of generative AI now. But yeah, it started in this very niche way where I was like talking to linguists and very worried about or like very interested in human language. Yeah.
So, on a broad level, what role does control play in designing or understanding AI systems, and why do you think it's important to develop and analyze AI architecture using control theoretic tools?
Yeah, so this is a very novel direction. I think that there is a lot of things for control theorists to do. I don't think control theorists have been in the mix during the development of AI, but I think it's time for us to jump into this work. I think that AI systems are engineering systems, and sometimes we forget because we hear people talk about AI systems as almost as having their own agency, as like being this free agents or something. but they're not. They're just engineering systems, just like a bridge is an engineering system or a plane is an engineering system. And engineering systems often, like we're able to trust them. Like that's why we can like drive over a bridge or board a plane. We trust them because these systems have some sort of guarantees or like at least in probability for their behavior. And I want to equip AA systems with the same type of guarantees and ultimate trust so that they're predictable and controllable. And it's not like we're at their mercy of their random outputs, but instead we have principled ways of controlling them. And I think that this is really important for society as a whole, but it boils down to an actual engineering problem. Just when we, in a very similar way that as when we learn to control planes, for example. So I think we're right in this era where we have to get to that last mile of controlling these systems, and control theory has a huge role to play. Yeah, that's where my work is at these days. Yeah.
So I guess moving a little bit more into the more technical side. So you've studied the dynamics of AI systems at various different levels of granularity, all through the lens of control theory. So could you give a bit of an overview of kind of what these different levels constitute and what their role is within overall AI architecture?
Yeah. So a lot of the times when I say, oh, we should control AI, people tell me, well, but AI is like such a complex system. How are you going to do that? And it turns out if you break it down into the different levels of granularity, you find dynamical systems all the way through that you can sort of control independently. So the first one, and this is my own naming of these parts. I don't know. Some of them are standard, but some of them is the name that I decided to give them. One of them is what I call the deep architecture. So when you have an autoregressive architecture, meaning you produce a token and then you feed back that token, or a diffusion process where you're going through denoising steps, every one of those steps, every one of those cycles that you go through can be seen as a time step in a dynamical system. So that could be a level of granularity where we find a dynamical system.
So just a basic AI overview for anyone who might be from a more traditional control background. So here, tokens are essentially the units of data that AI systems work with. So this could be words, parts of a word, patches of pixels, that kind of thing. And the process of feeding tokens back means that AI systems can contextualize sequences of data. So you can feed in a series of sentences and have the generated output depend on all of those rather than just considering each of them individually. Diffusion models are a type of generative AI architecture that are trained by adding noise to real data and getting the model to reverse this process in order to learn patterns. Very interesting, but not super relevant for understanding the rest of the podcast. So I'm going to leave links in the description if you would like to learn more for yourself. Another example of a deep AI architecture that you might be more familiar with is transformers.
But now we can open up this, say, autoregressive architecture, for instance, and we're going to have layers stacked sequentially one after the other. And now we can see each of these layers as a different time step in the computation. So we can see the evolution of the representation across the layers as a trajectory that we can control. So there you have another dynamical system. And then you can open up the layers and we find all sorts of components. I call them the surrounding components. And then these components are surrounding what I call the token mixer, which is often attention. It could be a choice for this token mixer. State space models, RNNs can be also parameterizations for this token mixer, and that can also be seen as a dynamical system. So you see, we keep opening up and we keep finding different dynamics that then we can control.
So just to add a little bit of context here, you can think of token mixers as the fundamental building blocks of AI systems. The most common examples are attention, which is what's at the heart of transformers, state space blocks, which make up state space model type architectures, and the recurrent unit, which is the backbone of recurrent neural networks, or RNNs. You can think of RNNs as very similar to standard neural networks, but the output of each neuron is fed back as an input. Now, these mixer blocks have surrounding components, which are things like skip connections, gating operations and pre-processing using either a linear or non-linear map. We won't touch much on this in this episode, but I'm going to link to one of Carmen's papers that analyses skip connections through the lens of control theory. So together, token mixers and surrounding components form a layer, and a bunch of these layers stacked together forms the overall AI architecture.
And above all of that is the interactions with the AI system. So if I'm talking to a chatbot and this is a dialogue, or if I'm interacting, say, with a robot, or the robot is interacting with the environment, all of that is also closed loop interaction that can be modeled as a dynamical system. So we have dynamical systems all the way through that we can hopefully control.
Before we go into the details, I wanted to clarify a bit of terminology. One of your early papers in this area looked at developing a unifying framework for foundation models, and you worked on another paper focusing on sequence models. So I guess, how would you define foundational models and sequence models? What's the difference between them? Is there a difference?
So I used to use the foundation models terminology more earlier. I think now I talk about generative models, which are models that basically generate new tokens. And I sometimes talk about sequence models interchangeably, even though that's not quite accurate, because there is some models that are not that process sequences but are perhaps not generating more of the sequence. But yeah, I think it's very context dependent, and sometimes the choices that we use when we write it down in the paper is based on the audience that we're going to have or the terminology that people talk about. I don't think there is a very established, rigorous terminology in the community so that these things have a clear-cut distinction. So yeah, a lot of the times I feel like it's still context dependent.
So for the purpose of this episode, you can think of sequence models, foundational models, and generative models as anything that generates novel content.
Yeah, I think this definition fits a lot of different systems, like language models or generative models, image models, visual language models, vision language action models for robotics, DNA models. All of these systems can be seen as generative models.
One type of foundational model that you've examined in quite a bit of detail are state space models. I know you've written a really good review paper on this topic, specifically kind of aimed at control theorists. So could you summarize what's meant by state space models within the context of AI, and what are their advantages over maybe transformer-based architectures that people might be more familiar with? Carmen's paper was titled State Space Models as Foundational Models, a Control Theoretic Overview. I would highly recommend giving it a read. Also, if you'd like to learn more about transformer-based AI architectures, there is an excellent 3 Blue 1 Brown video on exactly this topic.
So when I was talking about the token mixer, the state space models are a choice that people make for the token mixer, and they're tracking a state, meaning there is a state that is sort of remembering or keeping the past information that went through it. So this means we don't have to feed in every token every single time, because there is some sort of notion of memory through this state that is kept within the model. This is in contrast to, for example, attention, where it processes every token every single time, and that means that it doesn't do very well in long contexts, because it has it scales quadratically, basically, with the token length. And in contrast, the state space models are able to scale in a subquadratic way, because they don't have to process, they scale much better with context length.
So the terminology here is maybe a little bit confusing, because the term state space model can be used to refer to both the mixer block and the overall system, consisting of multiple layers of mixer blocks and scaffolding. So the mixer block is your classic linear discrete time state space system with ABCD matrices, and training of the involves involves learning the values of these matrices. There are various different ways of parameterizing these matrices to make this task easier, and the various pros and cons of each are outlined in Carmen's review paper. So I guess it kind of makes sense that state space models could be analysed using control theoretic tools, but you have also worked on a number of papers that look at kind of unifying or generalising various architectures. So why is this kind of generalisation or unification something that interests you or that you think is important?
Yeah, because again, I was talking about the dynamics that exist at the different levels of granularity, and in particular at the level of the token mixer. So if there is dynamics there, I think it will be really good for us to understand what are those dynamics. So in particular, what this token mixer does is, so we give it some sequence of tokens, and it produces a new token or a new sequence of tokens, and then we have benchmarks for this. And there is some behavior that it exhibits that we describe to be intelligent. So, for example, there's tasks where we're asking it to recall some elements of the sequence, or the needle on the haystack. Like there's tasks like that. And then when it outputs the right sequence of tokens for the given sequence of tokens that we gave it, we call that intelligent. That sort of fits the benchmark or whatever. So there's some trajectories that are intelligent, and then there's some others that are not. And so, what are the dynamics of intelligence? What are the dynamics that give rise to trajectories that we call intelligent? And I want to understand that fundamentally. Like, what is underneath these intelligent trajectories? And what are the ingredients that make for that to be the case? What are the ingredients that need to be present in the token mixer for this intelligent behavior to emerge? And I call that the dynamics of intelligence. And then I think that we can learn a lot about that by looking at, well, existing proposals in the literature that successfully achieve this task. If they successfully achieve this task, then they have somehow implemented the right dynamics. But now there's many different parameterizations that people have used for, or choices that people have made for this token mixer that give rise to this intelligent behavior. So what do they have in common? What are the underlying dynamics that is underlying all of these choices that lead to this intelligent behavior? So that's a little bit the idea.
So, in particular, one of your works in this area introduced what you call the dynamical systems framework that you use to compare attention, state space models, and RNNs. So, I guess could you give an overview of how this one framework was able to encompass each of these different model classes?
Yeah, I think that was like the technicality for this is actually not that difficult. We just use different techniques to be able to write these different parameterizations in our usual state space frameworks of A and B and C and D matrices. But what was interesting from doing this exercise is we found that there is some common structure, and I'll refer people to the paper to find exactly what I mean by this, but that we found some common structure between all different proposals in what the A and B matrices would look like. And then we also found that some things that were thought to be really important in one model class were not necessary for some other model class to be successful. And then what we found is that there could be cross-pollination between these different parameterizations. So for example, we found that particular choices for the B matrix, when adopted by a different parameterization, that leads a consistent improvement for that family of parameterizations, meaning that some parameterizations could learn from, or like could use some of the choices from the other parameterizations. So those were some of the insights that we found.
So I guess that is kind of starting to move the conversation more onto like designing kind of AI architectures. So a few months ago, I saw that you released a paper looking at how to design sequence models. So yeah, I guess what was the overall motivation behind this paper and what were the kind of concepts that you were looking into?
Yeah, so here we wanted to build on the previous work and try to see if we could come up with a unifying, perhaps more general way of looking at these token mixer choices, and then try to see if we could come up with design principles for them. In the sense that a lot of the times these choices are purely empirically driven. And people know that they have to normalize this one vector or that they have to do all these things, but some of the times those choices actually interact. And if you choose to have a particular choice for one matrix over here, maybe you don't need to normalize this vector over here. There's things like that that experts know very well, like people who do this for a living and come up with token mixer parameterizations for a living, then they already know all this tricks and choices and all of that. But we wanted to have an attempt at formalizing these ideas, and a lot of the times the formalization came down to control theory ideas. Like, for example, you want your A matrix to be stable, and if it's too stable, then you're going to forget really quickly. Things like that that link the ability that the model has to forget or the convergence and things like that. And yeah, that was our attempt at formalizing all of these possible choices that people can make when they design a token mixer.
So a kind of a key concept within this paper is that of coefficient dynamics, which gives a different, maybe a different way of viewing deep sequence models as dynamical systems. So yeah, I guess could you elaborate what this looks like? So I know you considered each token individually rather than kind of looking at how they're mixed. So I guess like what was the motivation for that?
Yeah, I guess that so the token mixer mixes tokens, and it does so by weighting each of the token with a different coefficient. Is just a weighted sum. But the key there is how you compute the coefficient that goes into each token, and for that, in order to compute that coefficient, that's where you use your queries, your keys, and your values.
So queries, keys, and values are the components that make up the attention block that we mentioned previously. However, because of the duality between different types of AI architecture, you can use these concepts to understand any kind of mixer block. In particular, these queries, keys, and values are all vectors generated by multiplying the input to the mixer block by a particular matrix, and these matrices make up the learned parameters of the model.
And so there is some interesting interaction between the queries, the keys, and the values that happen when you are going to compute the coefficient for each of the tokens. And that interaction that I alluded to actually has this dynamics that we could model and therefore come up with principal ways of designing depending on what your goal is. So if your goal is to forget some of the tokens, then you might want to be setting some of those coefficients to 0. And that was going to tell you something about how you should design the dynamics so that you tend to 0 quickly, depending on your keys and your queries, but yeah, more easily than perhaps if you're interested in solving a different task.
I just wanted to add in a little bit more detail on this paper because I thought it was super interesting and seemingly a very unique way of viewing AI systems through the lens of control. So, as Carmen mentioned, the output of the mixer block consists of a linear combination of your input tokens according to the model coefficients. And this paper viewed these coefficients as the output of a dynamical system for which the input is given by the keys of the model. So you have keys as the input, a linear evolution of the internal state, and then a non-linear readout map is used to map this state to the system coefficients. And Carmen and her collaborators were able to give additional insight to the problem of designing these kind of systems by examining their impulse response. So, moving on now from kind of analysis and design of these architectures onto how you actually control them. So, I know you mentioned earlier about kind of controlling language. So, you've written a very interesting paper looking at how to control text generation within large language models. So, I guess, like, what does it mean for text generation to be controlled?
Yeah, so that means imagine that you have a knob and you can turn it up and down on, for example, how toxic your generation is, or how happy or sad you want your generation to be, or how we also just 2 days ago submitted this paper on translation. So now I want my model to speak in English, and now I want my model to speak in Japanese, and now you turn up and down all these different knobs, right? And we also have this for robotics. So we also have a very similar work where we apply the very same techniques that we applied to language in a robotics context. And now we have this knob that tells us that you can turn off and on and say, I want the gripper to be really high or to be really low or to be open or to be closed, or I want the action to be really safe. So that is what it means to control a generation. It's like you get back that control instead of being at the mercy of what the model is gonna output. Or what's often the case is that you have your only resource is to just give it a prompt and ask it to please not be toxic and then hope for the best. Instead of that, you sort of have this internal access to the model that lets you modulate the response in a more accurate and controlled way.
So there's 2 points that I wanted to mention here quickly. Firstly, this paper assumes that you have access to some sort of off-the-shelf classifier that you can feed the output of your large language model, or LLM, into, and it will then give you a single metric that quantifies whatever you're interested in. So, for example, a single number quantifying how toxic your output is. The design of these kind of classifiers is an interesting area in itself, but it's not the topic of this particular paper. Also, a key distinction is made in this work between steering and control. So most papers in this area apply interventions to try to steer the output to be within some desired region. So, for example, to be below a certain level of toxicity. Steering makes this outcome more likely, but not completely certain. In contrast, control refers to enforcing constraints explicitly and providing formal guarantees that the model output will lie within the specified set of acceptable values. The question then becomes how you actually implement this kind of control in practice.
So a lot of the times in the literature for activation steering, people intervene in one or a few layers. And I alluded earlier to the fact that we see a dynamical system through the layers because we can look at how the representation evolves across the layers as a trajectory. And so if we have this control theoretic glasses on, then it would only make sense to intervene every single time, right? Like you want to control your dynamical system at every time step, or at least you want to have your controller ready to kick in at every time step. People don't think about it like that. People often look at what layer is this expressed the most, and then let's intervene just in there. So they almost give an impulse. And in this paper, what we wanted to emphasize is the idea of control, but perhaps what we mean by that is actually feedback, because we nudge it a little bit, say at layer 1, and then we let it compute in layer 2, and then we check, and we nudge it again, and then layer 3, and we nudge it again. And so this is, you see, this idea of unrolled feedback, and this lets you get away with a much smaller intervention that doesn't really disrupt the original dynamics of the system, but it's successful because you do it many times. You do as many times as layers you have, and it's often 32 times. So that's often enough for you to successfully correct the behavior without just introducing a sharp impulse in one or two of the layers.
So, in particular, Carmen's paper does this by explicitly framing the problem as an optimal control problem, where the control input corresponds to vectors that are added to the output of various layers of the LLM. And in particular, the aim is to apply as little control as possible whilst ensuring that the metric corresponding to your model output stays within the specified bounds. By minimising the control effort, you ensure that the generated output stays as close as possible to what the model would have generated without any intervention, as Carmen now explains.
So like what I mean specifically for the model is that you want to respect the dynamics of the model as much as possible. You spend so much money in time training these weights, so you have to sort of trust the choices that your model is going to make when it comes to choosing tokens, but you just want to be there to slightly correct that. If you disrupt that a lot, or say if you filter it out, it's as if you're basically discarding this thing that it costs you a lot of money to generate, actually, because it like training those weights was actually very expensive. So you want to take advantage of that as much as possible, And so that's why you want this minimal intervention, as long as it satisfies the zero constraints of, say, not being toxic or be happy or whatever. Yeah.
So another really interesting paper you've worked on in this area looked at the controllability of generative models. So I guess most listeners would probably understand controllability in terms of like standard classical control perspective. So how is controllability defined in the context of AI and generative models, and why is this important?
Yeah, so in this paper, we looked at what is it that you can get your model to say with just the prompt. So if you're in a dialogue type interaction and you're looking at a specific feature that you're observing in your output, so for example, how white is the background of the image that you're asking it to generate, then can you actually get it to give you like the white background, or does it start with something grayish and then you only get it to be light gray but never white? So this is assuming that you're trying to correct your model through a dialogue type interaction. And then, yeah, the controllability is, can you get exactly what you're asking for, or is that not possible to do with a prompt?
So you mentioned about like dialogue and dialogue processes. So how can this be viewed as a dynamical system?
Yeah, so a dialogue process can be seen as a closed loop interaction because you can see the user to be the controller, and then the system, the generative model, can be seen as a plant in a way. So the model is generating something, and then you look at the generation, that could be the model state. You look at that state, you observe the feature, and then based on the feature that you're seeing, you provide another input, which could be like, sorry, I didn't like it. Please try again, or please give me a wider background, or something like that. So this is you can see this dialogue process is a dynamic as a closed loop interaction, as a feedback interaction. And I believe in the paper we have a formalization of this. So I refer listeners to that.
So I noticed in this paper you dealt with probabilistic notions of controllability and reachability. So why is this necessary for this particular application? And also, like, how do these definitions, like, how do you have to modify them to be able to deal with probabilistic scenarios?
Yeah, so a lot of the times these models sample from a vocabulary of tokens, and so their outputs are often stochastic. This is true in both the language models that we looked at as well as the image models. And in the language models that we looked at, the vocabulary is still finite, but then in the image case, it's a continuum, right? Because like you can get basically any value for your pixels. So then, in the cases where we considered this probabilistic generation or this stochastic generation, then we had to add some additional considerations to the proof to make that hold. I mean, I don't want to get caught up into the super technical details. Yeah, a lot of the times the models are stochastic, and once we worked it out in the deterministic case, it only requires some more small technicalities to be able to capture the stochasticity of the models.
So another kind of key concept in this paper is sampling complexity. So I guess how many initial states you need to be able to, or you need to sample to be able to approximate your controllable set. So I was curious as to like what kind of numbers you've been dealing with in practice when implementing this with kind of real LLMs or other kinds of generative models, and what factors like influence sample complexity.
Yeah, I that's a really good question. I don't have the numbers on the top of my head. I believe the numbers are in the paper, so that always rules over what I say now. But I believe that we were sampling in total like around 1,000 different combinations of both context, because what matters there is the context that we have as well. Like if you've primed your LLM by saying hello, or you had a previous conversation, that matters. And then how you formulate your request also matters. So we tried different combinations of the context that we give it as well as the prompt that we give it. And I think we explore around a thousand generations, but I might be off by even an order of magnitude there.
I just wanted to explain this in a little bit more detail because I don't think I asked Carmen the right questions to be able to get across what's actually going on here. So, as you may already know, reachability refers to what regions of the state space you can steer the system to for a particular initial state. And a system is controllable if all of the states are reachable from all other states. Because of the stochasticity of this system in particular, this paper looked at constructing approximations of reachable and controllable sets by sampling regions of the state space. And this led to defining a so-called sample complexity bound, which quantifies how confident you are, given a certain number of samples, that you've constructed an approximation of the true controllable set to a specified precision level. And the reason this is useful is that it gives a tool to analyse and compare the controllability of different LLMs, as well as examining how various approaches to prompting impact controllability. So, moving on now to, I guess, maybe the highest level of abstraction. You've worked on, written a few papers on incorporating AI architectures into controlling physical systems. So, I noticed you did some work recently on controllability of vision language action models. So, I guess could you give an overview of what are vision language action models, why are they useful, why might they be a bit more complicated to analyse than LLMs?
Yeah, so these are models that take in a prompt, like a language instruction, and a visual input, usually an image of the scene. So, for example, you can imagine like a picture of a kitchen and then an instruction of please wash this dish or something like that. And then the model would output an action chunk. So we can think about it as a trajectory for the robot to execute. And so these models are pretty much end to end. Like they go directly from language and images to an action. And so the question of how to put guardrails in the middle of all of that seems pretty important because, again, these models were really expensive to train, and ideally we're able to take advantage of as much as possible of the knowledge that they've gathered through all the training data they've seen. So we don't want to discard their generations. We don't want to filter them out at the end, but we do want to steer them towards what's desirable for humans, like safety and so on. So yeah, that's the context of the paper. And the reason why these architectures are different is they're multi-model, and they have internally they have different like architectures within them. So the ones that we worked with, like the perhaps the most prominent one, which is called Pi, has a transformer type architecture and also a flow matching model that's attending to the transformer. So it's not just the transformer that we use for language models. In this case, the architecture is slightly more complex. That being said, turns out that you have a lot of leverage by just intervening at the transformer levels.
So, this paper introduced concepts of feature controllability and feature observability, which examined whether a particular feature of the robot output is controllable or observable at a particular layer of the vision language action architecture. And this is slightly different to the definition in control, because in control, controllability and observability are concepts of your overall system. Whereas in this paper, we're looking at, for example, whether you can apply a control input at a particular layer to force the feature of interest to remain within the desired region. The paper then uses these notions to learn so-called feature observers for a particular layer of the model, and this then allowed control to be implemented in a very similar way as to how Carmen applied control to LLMs, as we discussed previously. So I'd like to move on, like, kind of back to LLMs and the question of how to interface LLMs with maybe more traditional control approaches. So there are two frameworks that you've worked on, which I think you called narrate and demonstrate. So yeah, I guess starting with narrate, like what's the general idea behind this framework, and could you give an overview of the building blocks that go together to allow you to achieve the objectives?
Yeah, so this work happened before vision language models came out, and here we were exploring these ideas of how can we interface language commands with actions and movement. And this work explores how to interface an LLM with a standard controller that produces trajectories, and in particular, what's the best way of outputting some of basically translating language into something that is then used to produce trajectories. And what we found to be pretty effective is if we have the LLM spit out a cost function constraints that then we put into a standard MPC controller. So this was the gist of the paper narrate, and it worked surprisingly well at the time compared to state of the art.
So the overall architecture here consists of a language module and a traditional MPC-based control module, and the language module was subdivided into a task planner and an optimization designer. Now, the role of the task planner was to split potentially rather vague human instructions into a series of specific tasks, and then for each task, the optimization designer would formulate a cost function and a set of constraints to allow that task to be achieved. So a key benefit of this is that it reduces the need for specialists to explicitly formulate cost functions for specific tasks, which might be rather complicated. However, because the trajectory planning and control is implemented using standard control techniques, you can still impose predefined safety constraints, which means that even if your LLM does something a bit weird that you're not quite expecting, if you constrain your end effector to be in a particular region, you can be sure that the resulting movement is still going to be safe, even if it's not exactly what you were wanting.
And then with demonstrate, what we did is so this was still very reliant on the prompt and very fragile to prompt choices. So here we wanted to robustify this, and instead of having the LLM purely spit out the cost function, we collected enough trajectories to be able to have the features of the cost function be learned in that way, so that the LLM's job would just be to choose some parameters to go into the MPC problem, but not the full-on cost function or constraints. And this also enabled us to put in some sort of notion of safety, of a safety check in between all of that. And we did this by leveraging the geometry of the embedding space and how that can be mapped to the geometry of the features that one can collect or learn from demonstrations. So yeah, that's a bit the overview.
So I think you mentioned a little bit about ensuring safety, but I wondered if you could kind of elaborate a little bit more on that and how that you ensure that the system is safe and that you don't get kind of LLM hallucinations that might cause things to go wrong.
Yeah, so here we've collected demonstrations, and what that means is we've given the robot a command like pick up the red cube, and then we've demonstrated that by teleoperating the robot and having it to pick up that cube. And we did that many different tasks. I think we collected on the order of 100 different demonstrations. So then whenever a prompt was given to the robot that was very different from the prompts that it had been instructed to collect, we would be able to flag that by just looking at the embedding of the token as very far from the tokens that it's seen so far. And if that were the case, then we would not continue with the generation because we would see that it's perhaps out of distribution. So that was a way of measuring the out of distribution.
So that's kind of all of my technical questions. I've got a few kind of general questions on AI and then some more kind of less AI related questions. So there's, I guess, a lot of like concern and hesitation about using AI in safety critical systems. So do you think that the work you're doing currently and have done could allow AI systems to be used in these contexts? And also, like, what developments do you think are still needed to allow for AI within safety critical environments?
Well, I'm hoping that my work can contribute to that. I don't think that this is something that any one person or any one research group is going to accomplish. I think that this is an interdisciplinary effort. I think that yes, controlling the model during generation is really, really important, and that is how we have success in other engineering systems. But I also think that steps like verification after the fact are also really important, and I know a lot of computer scientists working on that and formal methods. I also think that auditing is something really important, and I know social scientists working on this. And I even have a lot of the times get the question of, okay, you're controlling your LLM to not be toxic, but who defines what is toxic? And I think that ethicists would have to come in and also talk about this and like have their give us their input on this. So I think that it's a huge multidisciplinary effort, and I do think that it's possible to have this sort of AI-driven decision making in combination with other very like bulletproof, reliable methods for decision making in safety critical applications. But I think that we're not quite there yet, and I think a lot of effort is needed to get us there. Yeah.
So I know there's been a little bit of hype recently on using LLMs to design controllers. I'm just kind of curious as to what your thoughts are on that.
Yeah, I think that, well, this is slightly similar to the work that I've done in Nerit, and I think that if you're aware of the embedding space and you put in guardrails and the generations for controllers and so on, or if you use some sort of safety filter or like downstream safety check, this could be effective, and it could take advantage of the flexibility of generative AI. I don't think it's necessarily concerning if done right, but I think there's a lot of choices that have to be made, and some of them would lead to a safe system, and some of them will not. So it really depends on the engineering choices. Yeah.
Okay, so I've got a few quickfire questions at the end. So firstly, are there any areas of controller AI that you haven't worked in yet but would like to?
Um, Yeah, I think I'd like to explore more what happens during training. I think that understanding training of AI, it's probably very much a controlled it could be seen, could be modeled as a controlled process, and I haven't done much there at all, but it's something that I definitely want to do.
Who is your role model within the field of control or AI?
Someone who really inspired me is Domitila Del Vecchio at MIT. I applied there for grad school, and I went for their open house, and I met with her. I was really impressed by her work. It was very interdisciplinary because it was at the intersection of control theory and biology, and I thought this was so creative. And I was very inspired by that. In the end, I went to Caltech instead, but I think that I always had her as an example of someone who works in control and something very interdisciplinary. Her book has been read by so many people, probably everyone working at this intersection. And so I definitely look up to her. Also, John Doyle is someone who I deeply admire. So yeah, I think I have a lot of role models, but I remember her being one of the first ones. Yeah.
So, if you're not already aware of Domitila Del Vecchio's book, this is simply titled Biomolecular Feedback Systems, and it contains chapters on all sorts of interesting topics such as dynamic behaviour and robustness, stochastic modelling, various biological circuit components, and design trade offs. Also, if you're interested in biomedical control, I'm going to link below to an episode that I recorded last year with Matthias Fu discussing his work in this area, as well as two very interesting episodes of the In Control podcast that cover similar themes on biomolecular feedback from different angles. I'll also link the episode with John Doyle there if you want to listen to that. Final question, what has been your favourite paper or project to have worked on?
I think my paper on working on understanding the difference between foundation models. This paper, I had just moved to ETH in Zurich, and I wanted to work on this intersection, but I didn't really know what to do. And I had this amazing collaborator, Jerome, who was a grad student at the time, in the group, and the two of us were meeting almost every day, discussing our ideas, and we went from nothing to eventually having enough understanding that we could write a few papers about this. And the whole process was really intellectually stimulating, and also it felt like we were both in this together, in this quest for knowledge, at the intersection of control and AI together. And that was a really nice process to do with Jerome, and we still have a collaboration since that time. So yeah, definitely very grateful for that experience.
That's all of my questions. Yeah, thank you so much for agreeing to this.
Thank you so much, Lucy.
So, in summary, tools from Control can be used to both analyse and design AI systems at various different levels of granularity, all the way from individual mixer blocks to the feedback interactions between a human and an LLM. Control gives a way to unify the various different AI architectures, allowing for systematic design and reducing reliance on empirical tuning. It's possible to control the output of large language models using tools from optimal control by adding a perturbation to the output of each layer to change the generated output just enough that it satisfies your constraints. You can also use control theoretic tools to analyse the controllability of large language models. And finally, AI systems can be interfaced with traditional controllers to ensure safety, either by using them to generate suitable cost functions and constraints, or by learning from demonstration. I really hope you've enjoyed this episode. I found it absolutely fascinating to research and learn about all of this work. In particular, I loved all of the different ways that AI systems can be viewed through the lens of dynamical systems theory. That's just so cool. Next month's episode I have not recorded yet, so I'm not entirely sure what that will be. I have a few guests lined up, all doing super interesting work from very different areas of control, so it should be good, however it turns out. Also, if you're based in the UK, I'm going to be at the Control 2026 conference in Newcastle at the end of June. If you're planning on attending, please come and say hi. I will be bringing my microphones along, wandering around, trying to find lovely and interesting people to talk to. So hopefully see you there, but if not, the next episode should be out on the 1st of July. Until then, I hope you have a wonderful month.